How's it going, Samarth? Can't complain, can't complain. Bit of a headache today, so we're keeping the lesson short. I actually pulled the data from the Wikipedia page, and I just fitted a function to it. So in... actually, I wonder if I have it open. Give me a second here. How's it going, Michael? Can't complain, can't complain. Yeah, I saw the weather was 12 or something like that, so I'm itching to get out for a run. I haven't gone out for 3 days, so I'm itching to get out there. Might take a nap first, though. We'll see. Yeah, so Samarth, so here, I think there's... Yeah, so there's a way to enter... Actually, here, let me flip my screen here. Can you see my screen on the YouTube channel here? Alright, you want to hop in there? Link is in the Hangouts. Yeah, here it is again. Here's loading. Okay, cool. Here. Okay, so the first part of this lesson, so 3.1 is actually I kind of have already sort of shown you guys this, and you guys have already been kind of doing it without actually having been formally taught it, just because it's nothing you can't already handle, and that's a concept of higher order derivatives. So instead of just considering a function and you just take the derivative of it, you can then take the derivative and take the derivative again, right? So you can build up a first derivative and a second derivative. And as we'll see, this actually has some pretty immediate applications to physics, right? So physics, we define the position, and then the velocity is the first derivative of position, and the acceleration is is the derivative of velocity, which means acceleration is the second derivative of position. Now, I think if you guys are at all planning on going into taking like a first year physics class in your programs next year, this is how physics is developed moving forward, right? So once you get past grade 12, you cover physics using calculus, which is really cool. And it actually, it makes the subject, in my opinion, a lot more streamlined and a lot more enjoyable to actually work with, right? So if you do enjoy physics now, just keep going with it. Next year, it even gets better when you start being able to use calculus to solve physics problems, okay? But back up a little bit here. Let's just warm up. Let's determine the second derivative of y equals sine 3x, okay? So to do that, I notice here, and actually you guys should be pretty well versed with this now. This kind of looks like something on your test yesterday. But here we have an outer function and an inner function. So I'm going to have to use chain rule here for my first derivative. So y prime will be equal to, so derivative of sine is cosine of 3x. But then because I have an inner function, I have to multiply by the derivative of the inside. Okay. So that means clean it up just a little bit. Cosine 3x. All right. Now to find the second derivative, I just take the derivative of the function that I just found, okay, of the expression I just found. So y double prime is equal to, so 3 just along for the ride. The derivative of cosine is minus sine of 3x. And then the derivative of 3x is 3. So I pick up another 3. So I get negative, and then I can collect the 3 with the 3. So negative 9 sine 3x. Okay. One thing, so this should be familiar. I think we've done pretty much something exactly like this before. I do not think I've introduced the notation for the derivative or the second derivative using Leibniz notation, so using the dy by dx. So we could also briefly talk about that. So if I redo this exact same question but using dy by dx notation, I would have the derivative of y with respect to x. That's going to be equal to 3 cosine 3x. Okay. Now to indicate the second derivative, what I do is I do d squared y by dx squared. Okay. So the second derivative of y with respect to x equals minus 9 sine 3x. Okay. So just some notation here. Okay. Now the reason why personally, I do prefer this notation, the Leibniz notation. When you guys get to second year calculus, you're going to be dealing with functions that are dependent on more than one variable, right? So for instance, you could have y, or let's say you have a function f, and f is a function of x and y, right? So you have a multivariable function. Now, when you take the derivative of this function, you have to specify what derivative you're taking the function with respect to, right? So you could have something that looks like df by, or d squared f by dx dy, meaning you take the derivative first with respect to x, then you take it with respect to y. Okay, so this is often, you will definitely see this if you keep going with math, but that's sort of why I prefer Leibniz notation for this kind of derivative. But again, these two things mean the same thing, right? It's just a different way of expressing it. Okay. Any questions about that, or are we doing pretty good so far? Okay. Yeah, so as I mentioned, higher order derivatives play an important role in physics. So as we saw in chapter 1. Oh, you're doing okay? You're doing good? Okay, so yeah, as we saw in chapter 1, I think it was section 1.3 or something like that. Velocity is the rate of change of the position function with time, right? And then obviously we built up the concept of a derivative. So velocity is just the derivative of our position function with time. Okay, so that's where this formula came in. Now what we're introducing is the concept of acceleration. So acceleration is going to be the derivative of velocity. Acceleration is the second derivative of position with time. So d squared s by dt squared. Okay. And so let's work through an example on that. Okay. Here we have the position of an object that's moving along a line is given by 6t squared minus t cubed, where t is some number greater than 0. Okay. S is in meters and t is in seconds. So first things first, let's determine the velocity and the acceleration of the object at t is equal to 2 seconds. So to start with this, we're initially looking for the velocity. So the velocity is given by the rate of change of position with time. So the derivative of 6t squared minus t cubed. Okay, now I take the derivative, so I bring this is just a basic polynomial, so I just use my power rule here. So I bring the 2 down, so that gets me 12t to the power of 1, then minus 3t to the power of 2. Okay. Now to get my acceleration function, I just take the derivative of the derivative I just took, right? So acceleration is given by the second derivative of the position function, which is just the derivative of our velocity function. Okay, so really what I'm doing here is I'm taking the derivative of the function that I just found, the 12t minus 3t squared function. All right, so again, this is just an easy polynomial, so I just take the derivative just as I normally would. I get 12 minus 6t. Okay. So now I have an expression for both the velocity and the acceleration, which is great. This question is specifically looking for the velocity and the acceleration of the object when t is equal to 2 seconds. Okay, so all I have to do from here is I just have to plug in 2 into both of these. Okay, so v at 2 is equal to 12 times 2 minus 3 times 2 squared. Pop out my calculator here. I get a value of 12. Okay, and my units here for velocity, because the, going back up to the question here, I'm told that the position is in meters and the time is in seconds. The unit here is 12 meters per second. Okay, now I'm going to do the exact same thing for my acceleration function. Okay, so my acceleration function at t is equal to 2 is equal to, t is equal to 2. Is 12 minus 6 times 2. 12 minus 12 is 0. Okay. Now the units for acceleration, they are meter per second squared. Okay. Okay. So let's go back to the question here. So we answered the first one. That's good. At what time is the object at rest? Okay. So in order for the object to be at rest, the key word here is rest, which means the velocity of our object has to be equal to 0. Okay. So at rest means the velocity is 0. So really what we're looking for are the t values when our velocity function is equal to 0. Okay. So what I'm going to do for the second part here is I'm just going to copy the velocity function that I found from part A. So I know my velocity function v at t is equal to 12t minus 3t squared. And what I'm curious about is when this thing is equal to 0. Okay, when my velocity is equal to 0. By setting it equal to 0, I'm figuring out when the particle or when the object is at rest, right? So when the object is at rest. Okay. So now we have this quadratic equation. We're just solving for when it's equal to 0, right? So really what we're doing here is factoring, right? It's in standard form. We're trying to factor it to figure out what the zeros are, all right? Luckily for us, it's a pretty easy factoring job. So I'll factor out a 3t. And when I do that, I'm left with 4 minus t is equal to 0. So I actually get two solutions here. The first solution comes from 3t equals 0. Which just tells me that t is equal to 0. Okay, so when I start my stopwatch, this particle is just at rest, right? It's not moving when we start the experiment. And then the particle will do something, right? It'll start moving, it'll start accelerating, and then at t is equal to 4 seconds, right? Because 4 minus t is equal to 0, which tells us that t is equal to 4. The particle will then again be at rest, okay? So we get 2 points or two times at which the particle is at rest. Okay, so we summarize. Therefore, the particle is at rest. At rest meaning v is equal to 0, at t is equal to 0 and 4 seconds. Okay. So the key word for that question, at rest, is essentially synonymous with v is equal to 0. Okay. Okay. Let's keep it going here. So this next part here, in which direction is the object moving at t is equal to 5 seconds? So what we have to remember is that this object is moving along a straight line, right? So it's doing something like this, right? It's oscillating back and forth or something. We can see here it's some sort of cubic function, right? Now, when it's moving to the right, let's say to the right is positive, that tells us that the velocity of the object is going to be a positive number. So when the object's moving to the right, the velocity is going to be positive, and when the object is moving back to the left, the velocity is going to be negative. So really what we're interested in here is what is the sign of v at t when t is equal to 5. That's the way that we're interpreting what this question is asking us. Okay, so in what direction is the object moving at t is equal to 5 seconds? Really, we're just trying to figure out what the sign of v is at t is equal to 5. Okay, so let's get to it. So again, I'm looking at my velocity function, and I'm interested in what's happening at t is equal to 5. So v at 5 is equal to 12 times 5 minus 3 times 5 squared. So that's 60 minus 3 times 25. So 60 minus 75. So it's negative 15 meters per second. Okay, and what that tells us, therefore, the object is moving in the negative direction. Okay. So the sign of the velocity function tells us which way it's moving. Okay, did I have one more question here? Oh, last part here. When does the object return to its original position? So first we have to figure out, okay, well, the original position comes from when s at t is equal to 0, right? Because if I plug in 0 in for time into my original position function, I get 6 times 0 minus 0, which is just 0, right? So the original position, or the initial position, is just 0, okay? So what I'm interested in this last part, this part D here, is I just want to know when the particle reaches a position of 0 meters again, okay? So let's wrap that up. So D, we want to know when our position function is equal to 0. So I'm just going to copy the position function, 6t squared minus t cubed. Okay. And essentially I'm going to do the same exact thing that I did for the velocity function up here. When I wanted to figure out when it had or when it was at rest, I'm going to do the same thing. I just want to figure out where the position is 0, so I'm going to factor. Okay, so 0 equals t squared times 6 minus t. All right, so this one gets me t is equal to 0. That makes sense. That's my starting point. Okay, so that solution should be pretty clear. And the other solution is at 6 seconds. So when t is equal to 6 seconds, we also get back to our original point, okay, our original position. All right, so I know there's a lot going on in that example, but hopefully, again, as you kind of do more of these, once you get a couple going, it puts you back in the mindset of things that we were just talking about, right? Like reference frames and understanding which way things are moving and when things are at rest and all those things that we inherently have a good understanding of from physics, grade 11 and 12 physics. Hopefully, as you get more into this, you'll kind of, all that'll hopefully come back to you. All right, next example is pretty similar. We want to discuss the motion of an object moving on a horizontal line, given its position function, okay? So same idea. We want to figure out, actually this question tells us what we're needing to include in this little discussion. We want to figure out how fast it's traveling initially, how fast it's moving at the end, and then figure out whether or not this thing is accelerating at all, okay? So really it's just it's a pretty vague question, but we're just trying to get a sense of, we have this position function, let's try to figure out how this thing is moving, okay? Okay, so we know that our position function is equal to t squared minus 10t, okay? And so, I mean, we could do a bit of discussion here, right? So we could say, okay, well, where is it starting? Where is this particle starting, right? So let's plug in t is equal to 0 and figure out what we get. So we get 0 minus 10 times 0, which is 0, which means that the particle starts at the origin, or particle, object, particle, same thing. Object starts at the origin. At origin. Okay. And then let's figure out when it gets back to the origin, right? When it returns to its initial position. So that's exactly what we just did in part D of the previous example. So let's figure out when it gets back to the starting point, okay? So t squared minus 10t. Again, I can do a bit of factoring here. So t minus 10. Okay, which means it gets back to its starting point when t is equal to 10. Okay, so returns to starting point at t equals 10 seconds. Okay, and that characterizes our particle pretty well. One other thing we could calculate, if you notice in the question, we're actually given a interval over which this particle is moving, right? So we're essentially starting our stopwatch at 0 seconds, and then we're letting the object do something, and then we're stopping our stopwatch at 12 seconds. So we can actually also figure out our final position, okay? So s at 12. So where the object actually ends up at the end of the little experiment here. So 12 squared minus 10 times 12. So that's 144 minus 120. So that's 24. Okay. Therefore, the final position of the particle, the object particle, is 24 meters. Okay, in the positive direction, right? And so what these calculations have done for us is it essentially characterizes every bit of information we can get from the position function, okay? But we can also get some information from the velocity function, right? So let's take this, we'll compute a derivative, and we'll figure out what the velocity is, all right? So our velocity function is just the first derivative of our position function. So I'm just going to take the derivative of this thing, and I'm going to get 2t minus 10. Okay. And so this question is asking me, it's actually specifying that it wants to know something about the initial and the final velocity. Okay, so let's actually find both of those things. Okay, so let's find the initial velocity. So v at 0 is the initial velocity. And when I plug in 0 here, I get 2 times 0 minus 10. I actually get negative 10. Okay, so therefore the initial velocity is 10 meters per second in the negative direction. Okay. And we might as well also calculate our final velocity, right? So our v at 12, same idea, plug in 2, 12, minus 10, 24 minus 10, which is 14. Okay, so we see that the final velocity is positive, right? So at some point it switched directions. We can actually find that. We'll do that in a second. So therefore the final velocity is 14 meters per second in the positive direction. Okay. Initial, this was final. And just like we did for the previous part, we could also, it makes sense to ask when this particle is actually stopped, right? When it's not actually moving. Or another way of thinking about that, when the velocity is 0, it could mean that the particle is actually going, it's initially traveling this way, but then it comes to a stop, and then it's going the other way. So that's actually a really important thing to know, right? Is when the particle changes directions. Okay, so we can ask that as well. So here we can say we're looking for rest. So that's setting the velocity equal to 0. So we have 2t minus 10. And we can rearrange this thing. We get 2t equals 10, which means t is equal to 5. Okay. So what this tells us is therefore the object is at rest at t is equal to 5 seconds. Okay. Okay. So now we've kind of figured out everything that we can figure out about the velocity, right? We have our initial velocity, we have our final velocity, and we have the one point that the particle is at rest, meaning it's changing directions probably, okay? Last but not least, let's take our velocity function and let's figure out what the acceleration will be, okay? So the acceleration I find by taking the derivative of the velocity function, or another way of writing this is the second derivative of the position function with time, right? Both of those are the same thing. But really, I'm taking this this 2t minus 10 formula and I'm just differentiating it one more time. Okay, so I will get derivative of 2t minus 10 is just 2. Okay, and this is interesting, right? I calculated my acceleration and I found my acceleration was just a number. What that tells me is that the acceleration doesn't depend on time anymore, right? The acceleration is just some constant value. So we can conclude that. We can say, therefore, the acceleration is constant and equal to 2 meters per second squared. Okay. Whew. So that was a big question, but essentially, let's kind of summarize what we did, right? We kind of characterized our position, right? We figured out all the things we can figure out with our position function. We took the derivative to get our velocity function, then we kind of figured out a few more things about our object, right? And then lastly, we computed the acceleration. We found that the acceleration was just constant. Okay, so you can imagine that if you were doing an experiment, these are all quantities that you would definitely want to know, right? Like think to your physics textbook, right? The questions that you see in your physics class. Usually, we're asking the exact same types of question in our physics class, right? You have all those kinematics formulas to help you find all of these things, but one thing we realize is that those kinematics formulas are just kind of what we're actually doing here, which is kind of cool. Okay. So calculus makes physics a lot nicer, I would say, in my opinion. All right, let's keep it going here. So I have a question about a baseball. It's pretty much the same idea as actually no. You know what? We can go through this one. We might as well go through this one. Hey. Okay, so baseball is hit vertically upward. We're given a position function, negative 5t squared plus 30t plus 1, where t is equal to second, or t is measured in seconds. And so let's actually just kind of see what this thing is doing. So we have a ball, and it's hit upward. Notice that if I were to plug in 0 into this, right, s at 0 is just going to be equal to 1, which means our ball is starting at a value of 1. Now, this is just some quadratic function, right? So, and the quadratic function opens downward. So this is some sort of downward-facing parabola, right? So it's going to go up like this and then back down. And then the ball will end up somewhere around here. Okay? So part A here, we have to figure out what the maximum height of the ball is. Okay, so we want to figure out what's happening up here. Okay, or rather, when we get a value, or when we reach that max height. So we want to know what let's call that T max. We want to figure out what T max is. That's our goal for part A. All right. And so because we know what the height of the ball above the ground is, we know the function for that, that's s at t. What we're actually going to be doing, when the ball goes up, it goes up, 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 then it stops, which means the ball switches from moving up, which means it has a positive velocity, to moving back down, which means it has a negative velocity. Now, in the middle, when it's right at the top, the velocity is actually going to be 0, right? So that's going to be the way that we're going to solve this, right? So at the max height, we know that v at t is going to equal 0. Okay, so our goal for part A is just find the velocity function, set it equal to 0, figure out what time is. Okay, so we have s at t is negative 5t squared plus 30t plus 1, which means v at t is negative 10t plus 30. Okay, and we want to know when this thing is equal to 0. So rearrange this, I get 30 equals 10t, which means that t is equal to 3, or I guess t max is equal to 3. Okay. So that's cool. I'm able to find the maximum height. Now you definitely have done 3. I should probably include some units here. 3 seconds. Now you had definitely done some of these questions in grade 11 or grade 12 physics, and you use your kinematics formulas, and the questions would probably have been a bit harder than this, right? It becomes a lot easier when you're able to use calculus to do these physics problems, for sure. Okay. So that's part A done. Part B, we have to determine the velocity of the ball when it is caught 1 meter above the ground. Okay. And so what we want to do, this is actually a 2-part question for part B, right? So we want to know 2 things. We want to know, okay, first of all, when is the ball caught? So another way of saying that is when is s at t equal to 1, right? Because the ball is caught 1 meter off the ground. And then secondly, we want to know what is the velocity at this time. Okay. And now there's sort of 2 ways of visualizing this. One thing you could notice based on our graph here is that the parabola is symmetrical, right? So the 3 seconds that it takes to get to its maximum height will be the exact same amount of time that it'll take to get back down to the point where we catch it, right? And because it starts at 1 meter and ends at 1 meter, everything is perfectly symmetrical. So we should expect that our answer is actually going to be 6 seconds, right? But let's see mathematically that we do get 6 seconds there. Okay, so again, I'm interested in when is my function s at t? When is it equal to 1? Okay, so I have negative 5t squared plus 30t plus 1. All right, I'm going to move the 1 over to the other side here. And so I get 0 is equal to negative 5t squared plus 30t 30t. And then I factor, right? 0 is equal to negative 5t times t minus 6, okay? So my one solution I get is t is equal to 0. That makes sense. That first solution there is right at the moment that we throw the ball, okay? The second solution that we get is at t is equal to 6 seconds. And that's the one that we're actually interested in, right? That tells us when we get the ball back, right? When we catch the ball again, okay? So again, our symmetry argument right at the start there, thinking it was 6 seconds, it absolutely is 6 seconds. We get that exact value that we would expect, okay? Okay, now here's kind of the main focus of today. All right, so this is the important stuff now. All right, so we're into 3.2. This is the maximum and minimum values of a function on an interval, also called extreme values. Okay, so the setup for this problem, here we have a function f at x. Okay, now we're considering that function over some interval where x is between some value a and some value b. Okay, so that's the interval that we're considering our function over. Now, what this section is all about is finding the largest or the smallest possible value of our function over that interval. Okay. Now, there's some nice, the cool thing about these questions and the cool thing about optimization problems is there's always a set of steps and they never change. All right, so like once you do one problem, it's almost like you've done them all. The only thing that changes is the function that you're doing it for. All right, so although this stuff is pretty challenging and it's a little bit tedious, once you get good at it, you're not going to not be good at it anymore. Okay, so once you learn it right, you're good. All right. So steps here. First, we are going to compute the derivative of the function. Okay. What the derivative will tell us in step 2 here, when we set the derivative equal to 0, as we saw in chapter 2, setting the derivative equal to 0 makes the tangent line horizontal. What we're going to do is we're going to solve for all of the x values that give the derivative, give a value of a derivative of 0. Okay, these x values have a special name. They're called the critical values of our function. Okay. So any x value that makes the derivative equal to 0 is called a critical value. Once we find the critical values, we are going to plug them back into the function. So compute the value of the function at the critical values. And those give us the critical points. So the critical points is just a critical value with, or the critical value, the critical x value with the y value. Okay. Lastly, what we're going to do is we are going to compute the value of the function at f at a and f at b, okay? Because when we have a function, so I'm just going to draw a quick little sketch here. When we have a function over an interval, say between a and b, right? We might have, say, a point like that, and it comes down like this, and then it ends up like this, okay? So notice here that the only point where the function will have a slope of 0 is at this minimum value right here, okay? However, the maximum value will actually come from the point on the end, right? The end point, f at a, okay? So that's why we have to also compute the value of the function at these points, okay? I think this will all make a lot more sense once we actually go through an example, but I just want to kind of illustrate what's going on there. And then the last step here isn't really a step. Essentially, we compare all of the values that we've calculated, right? So we have all of our critical points, or the y values of our critical points, as well as the values of the function at our endpoints, so f at a and f at b. What we're going to do is plug, or just look at them and say, which one's the biggest one? That's our maximum. Which one's the smallest one? That one's our minimum, okay? So it's kind of a lengthy procedure, but again, you guys will be doing this so often that it'll just be second nature, or should be second nature by, say, like tomorrow, right? So do as many as you can, because tomorrow is going to be an important lesson as well, okay? Just some terminology here. So there are actually two types of maxes or mins, okay? So there's what's called a local max or min, which is the highest or lowest point of our function within a certain region of the graph. And then there's also absolute or global, also called global maxes or mins. And that's the highest or lowest point of the function over its entire domain, okay? So for instance, if we have just like a parabola, like y equals x squared, it has a absolute minimum, right? Because it's the lowest possible point on the graph, regardless of where we look on the graph. That's what it means by absolute or global, okay? The last bit here, maximums, maxima or minima are also called extrema or extreme values of the function, okay? All right, let's get into an example. Let's see how this is done in practice, okay? So here we have a function, f at x is negative 2x cubed plus 9x squared plus 4, and we're also given an interval for that function. Okay, so the interval is between negative 1 and 5, all right? So what I'm going to do is I'm going to follow this recipe exactly to get what the extreme values are. Okay, so step 1, I compute the derivative. So I want f prime of x. All right, so f prime of x is just negative 6x squared plus 18x. Okay, so there, step 1 done, easy. Step 2, I set the derivative equal to 0. Okay, 0 equals negative 6x squared plus 18x. All right, step 2 done, not bad. Then I solve for all values of x that result in the derivative equaling 0. Okay, meaning what I want to do here, because I'm dealing with a polynomial, I'm going to factor it. Right, so here I can bring it to negative 6x, and I'd be left with x minus 3. Okay, which means I'm going to have two critical x values, right? So I have x equals 0, that's 1. Okay, and I also have x is equal to 3. That's another one. Step 2, done. Okay, so I found my, I can even conclude, therefore my critical, or the critical values are x equals 0 and 3. Okay, step 2 is done. Step 3, I compute the value of the function at the critical values. Okay, so step 3, I'm actually going to evaluate the function, not the derivative, because I know the derivative is going to be 0. I want the value of the function, so I want f at 0. I want a number for that, and I want a number for f at 3. I want a value of what my function is. Okay, so what I do is I just plug in 0 into my function, so negative 2 times 0 cubed plus 9 times 0 squared plus 4, so I just get 4. There's one of my critical points, 0 and 4. 0, 4 is a critical point. Okay, and we'll do the same thing for 3. So negative 2 times 3 cubed plus 9 times 3 squared plus 4. So that's negative 2 times 27 plus 9 times 9 is 81 plus 4. I get a value of 31. Okay, so therefore 331 is a crit point. So I found my two critical values. I plug those back into the function. I have my two critical points now. Okay, step 3 done. Step 4, what I do is I compute the function at my two endpoints. Okay, so basically after this step, after step 3, I am done with the derivative. I don't have to consider the derivative anymore. Now I'm actually going to see what the value of my function is at the endpoints of the interval that I'm given. Okay, so in this case, my interval that I'm given is negative, or x is between negative 1 and 5. So what I'm going to do is I'm going to calculate the value of the function at -1, and I'm going to calculate the value of the function at 5. Okay, so same idea, I'm just going to plug in. So -2 times -1 cubed plus 9 times -1 squared plus 4. Okay, so I get 2 plus 9 plus 4, that gets me 15. Okay. And I'm also going to compute it at 5. So -2 times 5 cubed plus 9 times 5 squared plus 4. Okay, so -2 times 5 cubed plus 9 times 5 squared plus 4. I get a value of -21. Okay. Step 4, done. I have the value of my function at my 2 endpoints. Okay. Now step 5, all I do for step 5 is I just compare the various y values that I have now, right? So at my first critical point, I found a y value of 4. My second critical point was 31. And then my first endpoint, my left endpoint was 15, and my right endpoint was 21. Okay? And so this is, step 5 is just kind of like a concluding step, right? So 5, I can say, therefore, the absolute maximum is equal to, so the maximum value that I found was 31, right? And that occurs at x equals 3, right? So equal to 31 at x equals 3. And the absolute minimum value is, so if I look at my y values, I notice that the minimum value is -21, right? -21 at x is equal to 5. So I found my max and my min, okay? Which is pretty cool. So I've optimized my first function, all right? Now we could even take a second and just quickly graph this thing to see what we got was correct. Okay, so let's see what we can do here. I'll switch over to the, there we go. So I'm going to type in the function, right? So f at x equals -2x cubed, oops, plus 9x squared plus 4 over the interval -1 less than or equal to x, which is less than or equal to 5. Whoops. Started zooming, but I shouldn't have zoomed. Okay, there's my function. I can change my endpoints a little bit. So let's go -2 to 6. Oh, that's my y value, x values. -2 to 6. Y values, my y range I can make, say, -25 to 35. Okay, so this is what the function looks like. So here I can see, okay, I have a local minimum at x equals 0. I have my maximum was at 3 and 31. My endpoint that I found was -1 and 15, so that looks good, right? But notice that that's not the highest or the lowest point on my graph, right? That's just sort of, that's actually in between my 2 critical points, right? So this one doesn't really make the cut, right? It's not going to do too much for us, right? Similarly, 0 and 4, even though that is a local minimum, there's a value that's even smaller than that, right? The other endpoint here at 5 and 21, that value is even smaller than the value at our local minimum, right? So that means our absolute minimum is down here at 5, -21. Okay? And that's it. That's our first optimization problem. You can hear me now. Sorry. Okay. Yeah, so all I was saying, we have a current function. We have to find the maximum and minimum value of that current function. What this is saying here, we have to determine not only the times at which the current is at a max or a min, we actually want to determine the amount of current in the system or in the circuit at this time. Okay? Meaning we want to find both the critical values as well as the critical points. So really we're just repeating exactly what we did in the previous example. Okay? So step 1, I take the derivative, c prime at t. So I get negative 3t squared plus 2t plus 21. Okay. Step 2, I set the derivative equal to 0. Okay. Now here I have a quadratic that equals 0, right? And so I kind of need to factor this thing, all right? So I guess I could just use the quadratic formula, right? Let's see if it's an easy sum and products, or decomposition rather. So it'd have to multiply to negative 63 and add to 2. Okay, well that's not bad. That's 9 and negative 7, right? Negative 3t squared plus 9t minus 7t plus 21. Okay, then I factor by grouping. So negative 3t times t minus 3 minus 7 times t minus 3. So I get negative 3t minus 7 and t minus 3 as my two roots. Okay, I set these both equal to 0, right? So 0 is equal to negative 3t minus 7, which means that I get 7 is equal to negative 3t, which means that t is equal to negative 7 over 3. And I look at this thing and I say, what in the world, right? Because t can't be negative. Okay, so mathematically we found a solution that doesn't or can't really exist physically, right? If I go back up to the question, I note that the current formula is only defined between 0 and 5 seconds. And so this value here is inadmissible, right? Mathematically it works, but physically it's meaningless. So we get rid of it. We don't have to worry about it, okay? The other solution though, the other solution's fine, right? T minus 3 is equal to 0, which means that t is equal to 3, right? T equals 3. And that is a valid critical value, okay? So step 3, I find the value of my function at this critical value. So I want what c at 3 is equal to. So I just plug in 3 into my function. Times 3. So that's negative 27 plus 9 plus 63. I get a value of 45. Okay, so that's my critical value for that critical point, or that gives me the critical point for that critical value rather. So I'm almost done. That's step 3 is looking pretty good. Step 4, I need to evaluate my function at the two endpoints here. Okay, so I need to figure out what c at 0 and c at 5 is. Okay, so c at 0, well, c at 0, if I plug in 0 into my function, I just get negative 0 cubed plus 0 squared plus 21 times 0, so that whole thing is just 0. Okay. And c at 5, oops, c at 5, same idea, I just plug it in, so negative 5 cubed plus 5 squared plus 21 times 5. So that's going to be equal to is going to be equal to 5. Okay. So I'm now done, right? I've completed all the steps. Step 5 is mostly just like a concluding step, right? So therefore, the maximum current is 45 amps, and it occurs at t is equal to 3 seconds, and the minimum current is 0 amps, and occurs at t is equal to 0 seconds. Whoops. And that's that. I've done another optimization problem. Okay.